Participants, kindly turn off your camera. Mr. Lakshman.
Participants, kindly turn off your cameras. Uh, Good evening to one and all present here. So, on behalf of St.Mother Theresa Engineering College, Chairman or Principal, and the Department of Electrical Electronics and Electronics and Communication Engineering, I warmly welcome each and every one of you for today's session. Now, I am happy to introduce about the resource person of the session. Today's resource person is Mr. Daniel Satyaraj J. He is now presently working as assistant professor in Department of Triple E of Francis Xavier Engineering College. He has completed his BE degree in Karnia Institute of Technology, Coimbatore, ME from Government College of Engineering, Salem, and presently he is pursuing his PhD degree in Anna University in the area of microgrid. To his credit, he has 17 publications and 5 patents. He has rich experience of 17 years both in academic research and industrial experience. With this, I am happy to hand over the session to Daniel sir. Daniel sir, I request you to take over the session. Thank you.
Thank you, thank you, sir. So, good evening, everyone. Hope my voice is audible and the uh, screens are visible.
Daniel sir,
Sir, is my voice is audible?
yes sir, one kind request. Can you turn on your camera, please?
Yes, sir. Yes, yes, yes.
Okay, sir.
Yes, my screen is visible.
Yes,
Yes,
sir.
sir.
Okay, okay. Thank you. Can I proceed, sir?
Yes, sir.
So, good evening, everyone. Today, the topic for me is biomedical sensors. So, from the basics, I just want to give an overview about woods and biomedical sensors and what are the types. And at present, what are the types of biomedical sensors are there? And I also want to give a bit of touch in the area of research where the biomedical sensors are now heading into what are the things they have developed so far. So basically, a biomedical sensor, it is an sensing device that uses the basic transducer principle that will convert the biomedical signal into an measurable electrical signal. So it has to be associated with any human body or an animal or anything. Biomedical signal can be sensed, and from that it can be converted into uh, the measurable signal, and the associated system can convert that signal and store it and analyze it depending on the requirement of analysis, and from the action that required can be done through that signal. So biomedical sensors, it is an mandate requirement of nowadays scenarios. Everywhere we can able to see many type of applications. So the basic classification can be of non-invasive biomedical sensors where uh, need not to be inserted in any places, or it can be of minimally invasive sensor or indwelling sensors, and the final type of sensor will be invasive sensors. And in terms of the quantities that they measure will be of a physical sensors or a chemical sensor or any bioanalytical sensors or biosensors. The non-invasive biomedical sensors, they don't have any contact to the biological system from where we are measuring. The measurement will not have any touching into that one. And the sensor can be of it can measure any thing like heat or sound energy coming from an organism or an organ. It is a good example for non-contacting type of sensors or non-invasive sensors. It can be also placed on the body surface like skin surface. Examples can be of thermometers or any biopotential electrodes and strain gauges placed on the skins. And from that, the measurement systems can take the uh, values that required from the measuring quantity. And uh, these types of sensors, we are not going to have any contact, or we can just place it and we can able to measure the things. The second type of biomedical sensors is basically in between the invasive and non-invasive sensor. It is indwelling sensors, and it can be placed into the natural body cavity. Example, any oral or rectal thermometers. These type of sensors can use to measure any temperatures or any pressure transducers, and stomach pH sensors can also be an examples for this indwelling types of sensors. The final type of sensors are invasive sensors, and need to be placed inside the body of the system, the biomedical system, whatever the thing that we have to measure. And so we have to have some tissue damage also with the installation, and then only we can able to place it or fix it inside permanently for measuring the things. And we can measure various types of quantities. Based on that also, the biomedical sensors can be classified. Either it can be of physical type sensors, where we can able to measure the physical quantities like displacement, pressure, or any flow. It comes under the category of the physical sensors. The second category of sensors will come under the chemical sensors, and it is used to determine any concentration of chemical substance with a force. And the another type of sensor will be bioanalytical sensor or biosensor. I hope you already had an session on biosensors also, and it is also used to measure times or some type of internal quantities like enzymes. We'll also look these things within detail. For example, of physical sensor. Um, the first basic physical sensor that I have taken is the temperature sensor. So temperature is an important parameter, either in outside any systems. The measurement of temperature is a very essential part of it. In our human body also, measuring of temperature is very important. There should not be any rise in temperature to an abnormal condition. So measuring that, for example, we are using it. Normally we'll use this type of biomedical sensors for medical applications, means then it can be connected to within patient or things. So the temperature measurement is one of the important parameter that has to be monitored. And the temperature sensors like mercury thermometer, and it can produce a non-electronic output signal. So the commonly used electrical signal generating sensors, it has to be connected. For that, either it can be of thermocouples, thermistors, or resistant thermometers can be used for sensing those things. So the temperature can be converted into the common measured electrical signal. In thermocouples, it works based on the CPEC effect. Uh, if there is an two dissimilar conductors, so normally a voltage difference will be produced between these two similar conductors. For example, a hot and cold ends of two conductors can be there. So due to the difference in energy distribution of electrons, uh, to different temperature will be that. So based on that, the voltage magnitude will be generated, and it is purely based on the property of the conductor, the conductivity, work function, and the difference of voltage. All these things we are going to take into consideration, and the voltage change will be proportional to the temperature change for a given range of application, based on the type of conductors that we are choosing. And thermocouples can be used as an uh, sensors for measuring the temperature. And resistance thermometer is also an another basic kind of temperature measurement device, and it is also used for measuring the temperature with a variation in resistance of a metallic wire. So uh, if there is any increase in resistance of a metal wire with increasing in temperature, then we can measure that, and that resistance is measured, and with that the variation can be taken into account for the calculation and monitoring of things. So normally, the electrons in the metal, if that is given due to the any thermal energy is given, and then the movement will be very much rapid, and the oscillations will be higher, and collisions will happen in the atomic section. So what will happen? This will produce scattering of electrons, and this reduces the mobility of the electrons. So automatically resistance is inversely proportional to the mobility. The value of resistance is getting increased. And the resistance thermometer typically consists of any coil, any thin metal wire. Normally we'll use it, and for that we'll choose platinum wires, because it will give a wide and linear range of operations. So we'll use those type of wires. The resistance thermometer, it can also be called as a modulator or a passive transducer. So in order to determine the change, why we are calling it a passive, means we have to give an additional supply voltage, so that it can be uh, measure the value of resistance change. So the sensitivity of resistance also depends on the temperature coefficients resistance. For every material that we are going to use, it is going to get changed, and based on that, it will also the resistance will also change, and we are going to measure that also. Another type of measuring device, the sensor that we can able to see in physical sensor, will be thermistor. Can be also used as in biomedical sensors for measuring the temperatures. Normally, the resistance change will happen. The number of conducting electrons with increasing in temperature will normally happen, because due to the thermal generation, the electrons number of electrons increasing will also increase. So based on that, a thermal energy will happen, breakaway will happen, and it will be influenced by the external fields. So it is also similar to the resistance thermometers, but the difference between the thermistor will have up to 100 times higher value of PCR compared to the resistance thermometer. So these are the basic methods, other than thermometers, we can able to use as an measuring device for temperatures. And other type of sensors, physical type of sensors that can also be used for measuring the physical quantities are displacement and force sensors can also be used. Uh, it is associated with almost each other. If when displacement, the displacement can occur due to the force acting on that one. For example, due to an acceleration of a mass at a spring, that will cause an stretch of the string and the mass to move. So it is a displacement from initial 0 point and to the acceleration generated. These two are related, and by restoring the force of the spring. So based on this, the movement is happening due to the force. Also, we can able to measure, and due to the force, what is the displacement is also happen. These are the basic type of physical sensor. Other type of sensor is the second category of sensor is the chemical sensors. So um, many biomedical situation, it is necessary to know the concentration or any chemical activity of particular substance in biological sample. This sensors will provide the interface between the instrument and the specimen to allow to determine this quantity. Any concentration of thing, it has to uh, have in contact with that one, and that sensor will be taken into account of the concentration of the substance, and it will measure that one. And um, it can be tested in a laboratory, or it can be an uh, non-invasive or invasive type of sensor can also be taken. We're taking separately as a specimen and we are measuring it. It can be an non-invasive sensor. But if we are going to have an invasive contact, anything for a patient, we are measuring an any sodium something in the blood, then it can be an inbuilt sensor that can immediately send the values. So either type of sensor it can be used. So normally the biomedical sensors where we will use it like, will use it like this: a measurement will be there, a sensor will be there, and after that the instrumentation part will be there, like whatever thing that we are measuring, it has to be signal conditioning and processing has to be that, and data to be displayed, and it has to be communicated, and it is also to be stored. And based on that, the professional will measure the data, the readings, and if there is any abnormal reading is there from the instrument, they can able to find out, and the treatment along whatever things it's needed, it can be done. It is an one way of doing it, but not necessarily only for an hospital setup or a patient alone. This type of biosensor is used. For example, we can also use it for a sports person to measure what is the heart rate of an person when he or she is sprinting, or when they are in a playing in a thing, what is the heart rate, heartbeat. So much things also that it is one of the applications, and so much applications we can able to know. Even when normal routine life also we can use different type of biomedical sensors. Nowadays we are using it with our mobile phones also. This is an sample example, normally how different types of medical system and associated things are measured. Different kind of equipments or an electrodes can be used for measuring things. So, for example, blood flow range will be 1 to 300, and the frequency has to be used will be 0 to 20. Either electromagnetic or ultrasonic can be used for measuring the flow of blood. So this can be used in an sensor, and based on that we can use it. Or blood pressure, we all know, and any strain gauge arrangement, any cuff type of arrangement can be used. Cardiac output can also be there. Electrocardiography, any skin electrodes can be placed, and electroencephalography, it is ranges from 5 to 300 microvolt. The frequency is zero point 0.5 to 150 hertz, and scalp electrodes can be placed. And electromyography, any type of needle electrodes can be utilized. And these are the examples the types of electrodes that can be used, and the value of pH, 3 to 13 pH per unit, frequency is 0 to 1, and pH electrode is used. Similarly, PCO2 and PO2 electrodes can be used. In respiratory rate, any impedance type of things can be used, and temperature thermistor can be used, and it is up from 32 to 40 degrees Celsius. These are the sample things that is generally used as an application in medical systems. And other application for biomedical research, um, the biomedical sensors are normally used. Uh, if you're taking in research, we need data storage, data and for analytics and other things. So continuous requirement of data is needed. So from sensors, it can be given to things. Either it can be done remotely, sitting in a place using the IoT technology. We can collect the data. We can interface the sensor with any system, because nowadays sensors are after the signal conditioning and signal processing. It can be transmitted to any place. So normal uh, research is also, if it is in sample place, or if we are continuously monitoring anything can be done with, it is made easier way. So for biomedical research, many type of sensors are used. And patient care application is also another important area of biomedical sensors. Uh, these sensors are used as a part of instruments, and it can be uh, in a patient, or when they are moving and other thing. And we can able to measure blood pressure, oxygen saturation, body temperature, and any ECG also can be measured using this type of applications. And specimen analysis can also be used if you are using separate non-invasive type of sensors. And uh, uh, or any specimen can be collected, and it can be given to the sensors. The example is blood glucose analyzers are using these type of sensors. And sensors normally it is an uh, part of large and multi-component automatic blood analyzer. Uh, it is used in central clinical lab or any medical centers also. These type of sensors are normally used. And I have given also few examples for the biomedical sensor, some pictorial representations. Some bioelectric sensor, it is an wearable one. Finger electrodes are there, and wrist electrodes are there. If you want to measure the heart rate of it, we can able to measure using that. And it can be connected, or it can be transmitted to the required person, or we can also able to check it out how much thing is that. And it is based on electric signal only. It is an bioelectric type of sensor. It uses minimal amount of current to flow, and with that we can able to sense those things. And finger electrodes will also be there, and as well as wrist electrodes will also be there to ensure thing. It's just an wearable sensor, but uh, it is an advanced stage of it is a normal product available in the market. And for measuring other things, the flow of blood, uh, and the concentration in it, if you want to measure a particular thing in blood, that can be also used with the help of an biochemical sensors. We can use any devices to connect with it. For example, if you are using interfacing it with our mobile also, we can able to interface with it, and we can able to see the result through that. So it is mainly based on the concentration and the flow of things. Those things can be used with the help of this type of sensors. And another type of sensor is an bioacoustic sensor. in order to you can see the measuring electrodes placed in the hand. Whatever the place we need be, the device, the values that we want to measure can be measured using these type of sensors. And it is an example of EMG sensor. It is electromyography type of sensor. It has an motor unit action. Uh, so when a movement is taking, based on that, the vibration and the movement can be measured using this device. So normally electrical signals can travel through nerves, neuromuscular junctions. Any change in electrical potentials, or it can be called as a voltage, can be measured. So how the motion is there, whether it is fast, whether it is slow, any type of movement can be used with the help of this EMG sensor or electromyography sensors. And normally it is used in VR and prosthetic arms. It is normally used. And one more type of practical application of sensor is known as galvanic skin response sensor. So we can able to connect it with sensors. It is used to give the reflectiveness of our intensity of our emotional state, or any emotional arousal is that. So the how we are going to measure it, the skin conductance will be uh, directly related to the emotional regulation, and it is not under conscious control. For example, if you are scared or happy or any agitated or any we are in an emotional state, will increase in sweat gland and activity. Those things will immediately takes place without our without we know what. So those types of things can be used to measure, and this GSR sensor or galvanic skin response sensors can use to measure those things, and it will give the state of things. How intense is the state will be can be measured using this type of sensors. And uh, for measuring the heart rate, there are varieties of sensors are available. Any place we can able to use it. The chest strap heart rate monitor can be used. It can be placed along with the chest, and it can be fixed with the strap. And any air clip heart rate also can be used. It can be used for a sports person also. When they are running, we can able to measure it, or any finger, or it can be placed in an arm also. uh, these type of sensors are normally available. These sensors can measure the heart rate, and it can able to give the required value. And it can be also stored. Any abnormal value, any changes or any sudden things can also be intimated to the person, or we can also take any things. Another type of sensors, like the research that's going on, will be the skin attachable sensors are nowadays getting increased. I have taken few examples. It is one of the organic pulse oximeter and the OLED type of thing. So when the pandemic occurs, these type of sensors got evolved much, because we can't able to go and touch the person, we can't able to go and meet the person. So if we can able to fix the this sensor only once in hospital, then they can able to measure uh, the readings using the oximeter. So only this is a small type of sensor. It can be uh, placed in a nail itself, so it doesn't need any other thing. We are going to place it in this one, and we can able to measure the required thing. So the oxygen level and the heart rate, all those things we can, pulse also we can able to measure it, and it is attached with a nail one, so it doesn't need any other thing for the measurement. So next, another type of sensor, skin attachable sensor, is a flexible sensor. It can be connected with a nose, and it is a bendable one. It is used for the respiratory monitoring system. Unable to see the thickness of the sensor, it is very thin. It is up to 1 mm only. And the circuit also very much flexible, and from that cable is connected, and through that we can able to transmit the things. And from attaching things and carrying a bigger one, the research has gone much deeper to one minimized type of sensors, and the type of electrodes that is used in that sensor, and material used for that one, and the type of things like passive or active, with whether it requires any external supply, or how we can able to minimize the power requirement for that one, how we are going to supply that one, and to the extent of remote monitoring, remote action based on that measurement. All those things are the developing area of this biomedical sensors. And one more thing that want to give us the sensors that recently developed, it is PPG sensor, and it can be used in clothes, or it is placed in a car to measure the heart rate alone. So we can able to place it, and when we are driving, it can be uh, given, and it can be measured what is the type of heart rate. And as the smart thing is getting everywhere, smart city, smart vehicle and integrated things, it can also be transmitted to the uh, hospitals or any required emergency number. If a person suddenly feels his heart rate is not good and it needs to be taken care immediately, it can be shown with the help of this type of sensors. And skin attachable sensor, it is an interdisciplinary and fast growing subject. Many healthcare household applications, and any pandemics that happened recently, so these things of sensors are taken over in a longer aspect. So still it has many thing in development, uh, not only the aspect of COVID-19, few other things also, heart rate and other things also. It is an important thing to measure. So, temperature, pressure, the blood glucose levels, all those things are necessary. We also know, for example, initially we have to test our glucose level in our blood. We have to take blood out every time, and it has to be uh, uh, given to any lab or any hospital to uh, check it, and that has gone to the next level, like we can able to measure the uh, blood level with the basic of we can test using the measurements sensors. In a step we have to put our blood and it will show the thing. And now it has also gone further, like we can able to place an electrode in our body, and if you are we have to install an app related to that in our mobile, and if you are pressing it and if you are checking it, automatically it will show our blood level. So without much waste of time, and the time is very much reduced, and we can also able to check our health condition. The If we are feeling some uncomfortness, whether it is due to the sugar level or anything, we can able to check it, and immediately we can able to do that one. So that's an area. uh, uh, Not only that, in many aspects, like not only glucose level, the sodium level and other salt in our body, and things can also be measured using pretty much the sensors available, and focus is also that. And the biomolecules measured are limited. The multifunctional, the integrators are still in the trend. We can able to use, or we can choose any type of biomolecules which are not measured so far. And skin attachable sensors will help them. Different types of sensors are there. Any long time monitoring and physical indicators can also be in research focus in this biomedical sensors. And few sensors are already, as I told, it is commercially available. And uh, but it is not widely used. The cost is another thing. The flexibility, the lifespan of the thing is also another thing. So for the research can be used, whether it is skin attachable is tolerance to us, it is cost effective, it is minimized one, and it can be accessed by everyone. Even the uneducated person can able to use it. uh, those things can be done, and whether we can able to produce those things in a large scale applications is also another thing that it has to be done. And it can continuously monitor the biomedical characteristics. It will obtain a huge amount of data, and how to process and analyze those data. Application in medical care is a major problem. So far we have gone many fold with data, data analytics, the data processing. So much things we have gone, but still in medical data analyzing and things, a lot of scope for research is there. Any advanced processing algorithms can also be developed using this things. And other than these type of sensors also, remote sensor type of sensors for healthcare improvement is being used. For example, uh, if a patient cannot able to go to an hospital, if their hospital is not available or not some reasons, the electrodes or something can be placed. And if any emergency, or if any thing is there, it can be either sent to the doctor, or the person can able to monitor it, and preferred medicine can be taken. But uh, the development of these kind of sensors also pose some risk. For example, if we are treating something in an hospital, the expert person, the doctor will always be available, and they will test, and they will give the required medicine that has to be taken here. And he also knows the other indicating parameters also. So based on the severity and condition, they will give. But the same level of severity will not be there. For example, if you are taking a medicine for a cold or something, if doctor is giving it for 5 days or more than that, we will not take it. Few will not take it seriously, and for one day or few days only they will take it. But the required amount of course of medicine has to heal the disease. So the required amount has to be there. So those negligence can also be a problem. Another thing will be the safety of the patient. For example, if an remote area is there, and data is there, everyone, if everyone can able to uh, access that data, it will be hard for one, hard for it will be an hardest one to protect that one. So again, like the normal cyber security and those things related can will come also into this also. So uh, we have to ensure the safety of data that is being collected. It should not be leaked, or it should not be improperly analyzed. So those things can also taken into account. And uh, other type of sensors is also that, like not only for humans, for plants and for animals also. It is that, for example, an herd is that of a cow herd is there, means how many is there, how it is eating, what is the eating pattern, whether we can able to measure the motion, how it is moving, whether it is sick. Those things can also be collected by implanting some type of biomedical sensors. The motion sensors can able to measure the movement of things while eating, while moving from one place to another. How that can use for research for further enhancing the things. Similarly, for plant also, so many sensors are available. How previously it was like the image processing data will take a snap of it. If there is any problem in it, then we can able to find the solution, and we can use it, uh, access it remotely. Now so much type of skin type attachable sensors, or any other movement, or any other things can accurately measured. Those things can also be there, and it can able to improve the things related with agriculture and other things also. So biomedical sensors will have a major impact in future. Lots in scope, lots in area of research is also that. uh, any from basic electrode till the type, the sophistication of using that sensor, size, weight, all those things, and any type of algorithms that can also be factors to be considered while we are doing the research. So that's all my presentation. If you have any queries, you can ask me, or we can able to go for the next session.
Sir, wait a minute.
Sir?
Wait, sir. Participants, do you have any queries? If you have any queries, kindly ask. Participants, if you have any queries, kindly ask.
If there is no queries, thank you everyone. I just want to thank the coordinators and the St. Martha's Engineering College and the team. And for the patient listening, I want to thank everyone. Thank you.
Now, sir, thank you so much, sir. Your presentation was wonderful. So, thank you.
Thank you, sir.
Participants, kindly join the session by 7:20. Now you can leave. Participants, the next session will start at 7:30 p.m. Thank you. Participants, one kind announcement. We will also post the same in the WhatsApp. That is, the resource person has some other engagement, so he is going to join the session by 7:15. So we already said that according to his request, we told that 7:30. Now he said that he will join by 7:15. So kindly be ready. Don't leave the car. Once again, I am telling that the session will start by 7:15, 7:15, and all of you are requested not to leave the car.
Good evening, everyone.
Rajesh Anand, welcome.
Hi.
ராஜேஷ் ஆனந்த் கொஞ்சம் வெயிட் பண்ணலாமா?
Oh, no problem. It's okay, fine.
ஓகேடா. ஓகே ஓகே. டீடைல்ஸ் கொஞ்சம் அனுப்பிச்சிட்டியா?
Yeah, I sent already. Yeah. அனுப்பியிருக்கேன் மெயிலில்.
Have you sent it through mail?
Yes, yes, I sent just now. Maybe 5 minutes back.
ராஜேஷ் ஆனந்த்,
Yes,
while
Ayappa.
talking, கொஞ்சம் kindly can you switch on your camera?
Yeah, sure, I can switch on.
Okay,
You can see me.
thank you. Okay, we're talking only. Now you can turn it off.
Can I start?
Uh, 85 participants are only there, so we shall start by some, what is it, 7:25, 8:25. Okay, then, okay, va?
Yeah, that's fine. I'm
Okay,
pretty okay with
thank
it.
you.
It's fine.
Rajesh Anand, shall we start? Rajesh Anand?
Yeah, yes, Ayappa.
Okay. So, good evening, all participants. So, we are happy to start the second session. Once again, a warm welcome to each and everybody. The resource person of second session is Mr. Rajesh Anand K, and he is working with GE in Dubai as a grid automation manager. So, I am happy to share a brief introduction about him. He completed his BE degree in Electrical and Electronics Engineering from Anna University during the year 1999. His experience spans over 23 years in the field of power system protection and automation, covering process industries, power plants, utilities. First, he started his career with Madras Cements Limited as a graduate engineer in the year 1999, with roles and responsibilities in operation and maintenance of transformers, motors, switchgear. Then he worked for various process industries. During the year 2004, he joined Alstom as commissioning engineer, in which his roles and responsibilities included protection, during which he was involved in settings calculation, testing, commissioning, and protection relays used for generators, bus bars, and transformers. In year again 2006, he started working for Awesome Protection Training Team, conducting various training programs for them. He has conducted application and protection of power system courses for various utility and industrial customers. He has joined General Electric during 2008 and currently leading the protection and application team of Middle East, North Africa, as well as Turkey regions. He has involved in the field of protection and applications, setting calculation, analysis of protection relays. He is also his interests also include wide area monitoring projects and digital substation solution. So we are happy to have him as a resource person. So I hand over the session to him now directly. Rajesh, Anand, you can take over.
Thank you, Ayappa. Good evening, everyone. I would like to thank the management and principal of Mother Teresa Engineering College, and my sincere thanks to the head of the department and the event coordinator, Mr. Reegan. Of course, my heartiest thanks to my friend, Mr. Ayyappan, who's my classmate and beloved friend. And it's my really honor to be here in this forum discussing about topic of sensors in the digital substation. Hope my voice is audible, and let myself or the event coordinator be notified
Yes,
in
sir.
case if
Yes,
you
yes, it is
in
happening.
case if you have any concerns on the audio or the slides. Okay. So let's get into the topic. Today we will be discussing about the digital substation, what a digital substation is, and what are the sensors used in a digital substation. Why do we call that as the sensors? And what is differentiating a normal substation to a digital substations using these advanced sensors? And in this category, we will have first on the instrument transformers, or you can say compact optical sensor intelligence, we shortly call as COSI. So COSI sensors, we will discuss how it is deployed in digital substation. It is not necessarily COSI. We will also discuss about Rogosi sensors, buccal cells, CMO. There are some advanced sensors in digital substation. Then we'll switch on to the monitoring and diagnostics of transformers. And of course, this can be used for any other bushing as well. So we'll discuss about the sensors used in the substations, where it will be very helpful for us to monitor, and what this transformation helps in terms of operation, in terms of maintenance, in terms of sustainability, and how this transforms to a reliable power system network. It's not only the sensor, we will also discuss about the applications. so that you can relate what you're seeing to the real-time world. And the details what I'm going to share is a part of the normal offering, which as a company, which we offer as a technology, which is there. So which means these technologies are already in the stage deployed in the substation, or maybe it is in the proof of concept. Mostly what I'm going to talk is already well versed used in the substations. So you can find, if you want more technical details like a manual, you can always find in our website. Let's get into the topic. So our topic starts with digital substation. So what is a digital substations? We all know substations. Most of you are, I believe you have got an idea about substations. And of course, we have got many experts throughout the country who are already in the field of power system. So you're all very well aware of the substations. Why it is called digital substation? So in digital substation, the parameters what we measure conventionally in analog form will be converted in the digitized format right from the source, or maybe in between a converter. So let me put it in that way. So for example, if you have a voltage, if you have current, so this voltage and current normally it comes from the voltage transformer or a current transformer, which is essentially an electromagnetic uh, winding with the coupling. By measuring the voltage, we step down the voltage for voltage transformer, and we step down the current for the current transformers. So this works on the principle of induced EMF and the flux linkage to the cores. Of course, then it is wired all the way to your panels or your control room. So you will have hundreds of wires or thousands of wires running between the station to your control room on the protection devices or the control devices or the measurement device. So in terms of monitoring and controlling a substation, you need to measure it, to monitor it, to control it and protect it, and use that data for any kind of maintenance, or you can use that for any further improvement what you need in the network. Okay. So in this concept, how we are going to digitize? We will digitize the voltage measurement. We digitize the current measurement using the sensors. So these advanced sensors uses different technology to convert it to a scale down parameter. Of course, why these instrument transformers are used is to mainly scale down because it can be a 400 kV, or it could be a possibly 1200 kV or 33 kV. So that's all at high voltage. You need to step down to a value which you can comfortably work, and you can monitor, you can filter the components, you can monitor the harmonics. So for all these things, you need to scale down. So these current transformers and the voltage transformers will be digitized. So the moment we digitize, you can see in this picture. So the one in the top has got this copper color wires, which emulates the wires which runs thousands. So once you convert it to digitized format, then you have some advantage. Okay. So this depicts a control room, a relay room, and a control center, which can be hundreds of kilometers away from your location. Okay. So how it works? Okay. It's all digitized using various sensors. So why do we do that? First, it's mainly for the safety. Okay, so it is safe because you convert everything to a lower digitized quantity right from the source. It's safe. Unlike a current transformer output or a voltage transformer output, a risk of open circuit or a risk of 110 volt being handled arcing in hazardous environment. And apart from that, it will be rich in data. So once you digitize, you can have a multiple instance of the same data at multiple locations. If it is analog, then essentially you may require more analog sources, which means more cores of CT or multiple cores of VT. Just to recollect, CT current transformers, VT voltage transformers. So once you digitize, and once it is in the TCP/IP layer with a specific protocol called 618.59-2, so you can have multiple instance and at multiple levels. So in the coming slides, you will come to know how the sensor provides a better data with better accuracy, avoiding many issues. And it is redundant. You can easily achieve redundancy, and it will be flexible for you to use. And of course, considering the environmental requirements, the sustainability requirements, it will have a lesser space. It will contain lesser space. It will consume lesser copper. And of course, multiple cables, what you normally use in the network may not be required. Okay? And then it will be interoperable solutions, which means you can have different types of vendors and easy expansion. So interoperability is something essential once it comes to a long-term operation. where we need to use multiple vendor across a substation, so that you can have a better competition and you can also have a better operations with the multiple vendors. So it's all follow a specific standard called 650, whereby you can have the full-fledged advantage. So what all the key differences what you will see is it will be a low power transformer, which you will see how that works, the sensors. And the second one, you'll have a very few fiber optic cables rather than having hundreds of wires. So you can see on the right corner, or you can say the right side, you have one device which has got two fiber optic cables. So RxTX, two pairs we have, instead of wiring hundreds of wires being terminated here. So all are digitized. So you will have a simple box with a couple of wires, fiber optic wires, which will have all the data required for the substation. Then you will have all the data in digital format, and it is a digital acquisition of data, and it will be easy for us to use. And then it will be integrated architecture instead of discrete. So the moment you digitize, we are not only going to digitize only the parameters of voltage and current, we'll be digitizing many other sensor like what we have in the transformers, or including the ambient temperatures, or including the thermal cameras. So there are many parameters will be digitized. So you will have integrated architecture. In one single HMI screen, you can have multiple information monitored. Of course, you will have a single overall distributed control system. It will be rich in data. Substation footprint will be less. The one on the left bottom corner is a substation control room, which used to be at least 15, 20 times bigger than this. As a prototype, it was done to have one substation control panel control room in a container. So this was one prototype project which was done. The one on the left bottom corner, what you are seeing, is a typical layout how a container can be used for a control room. So you can imagine there is no foundation. It can be a prototype made for certain functions, and you can move from one place to another place. And there are multiple advantages for engineering solutions. So your panel diagram will be much more standardized, and there will be a lot of logics and the interlocks defined in the software rather than in the hardwires. Okay. And the 10th one is very important. The moment you have all the data available in the digitized format, it is easy to track it, monitor it better. You can have a better condition based monitoring rather than having an annual routine maintenance without a need, or sometimes we may miss some major maintenance requirements. So in digital instrument transformers, which we call as a sensors, so these sensors are essentially scaling down the voltage. The sensing function will be mainly for current and voltage. Conventionally, what we will have, so the left one is a CT. So now you have got a donut-based Cauchy sensor. So this sensor is basically operating on Faraday's optical law. You can say optical effect for when you have a flux in the core. Okay, so when you have a flux, there will be a polarized light being sent in the donut core, and you can imagine it weighs hardly 15-20 kgs. A conventional a core of the CT weighs hundreds plus kgs. Okay, so it's only insulation which is required. Otherwise, you can use a simple mechanism like a donut optical CT sensor, what you see on the left side. Similarly, on the right side, we will have a VT. Then the output from the device will be a proprietary data, so which will be on optical. Yeah, which will be on optical. I'm hearing some noise. Why? Yeah, please mute yourself. Yeah. So you will have the data available on optical proprietary protocol. Then there will be a small numerical merging unit, and that will convert the data information to 659-2. So essentially, that will be complying to the protocol and the standards. Okay. So this is a look and feel how a conventional instrument transformer would be. Okay. So when you have for non-conventional, then it becomes altogether a simple one. Simple sensors, which looks like this. Okay, so this is look and feel of the substation, where you have hundreds of wires under the trench, because we need to carry a lot of information, currents, voltage, sensors, tripping commands, measurement information, and you need to have this information to multiple locations. So this data will be converted to fiber. So that's the whole idea of having this particular sensors. In the sensors, you will have multiple different types of sensors. One is based on optical Faraday current measurement, and then we have the CVT based sensors, Rogowski, and we will have different applications. So the bottom picture shows the real location, how it is mounted. Okay, the Rogowski based sensors for current measurement or capacity based voltage measurements, optical COSI, optical sensor based
Will you
current
convert?
measurements. Please mute yourself. So then we have multiple options for these sensors in different applications. So what you will have terms across this particular discussion will be low power instrument transformers. You have electronic voltage transformer sensors and optical current transformer sensors. Of course, normally CIT means the conventional instrument transformers. These are all the terminologies which you will hear in the domain of optical CTs or non-conventional CTs. How it works. Okay. So here we will have all these devices which will have either optic based or Rogowski based in a similar form, which will be closer or which will be mounted in the primary system, okay, which will essentially link to the flux, or it will have the voltage measured at a low voltage by the CVT, and then it will be wired. Okay, so it's how it is located. If I go inside the device, how it looks. When you look at a current sensor, like with a Faraday effect, okay, so what we will be doing, if this particular plane, okay, is your light, it's a polarized light. If I can have a well-defined polarized light of a certain well measured and calibrated light, if I can send it across in a flux environment, magnetic flux environment, the polarized light will have a shift based on the level of magnetic flux. So that's a very simple theory, Faraday optical effect due to the magnetism. Okay. So this magnetism will impact the polarized light. So these sensors, we will send a well-calibrated light which are polarized, and the flux in the primary conductor will shift the angle based on the magnitude of the current. So the flux is directly proportional to current. So ultimately, the light which is sent inside and the light which is coming out will have the shift based on the current. So through which we in turn convert the sensor to measure the magnitude of the current. So this explains how we will be sending the current all the way inside our medium, inside that particular conductor. Okay, so this conductor will be carrying current. So we will have a donut shape. So the look and feel would be like a donut. And then you will have the output of the current, which will have a displacement or the shifted polarized magnitude. And the sensor will come to our proprietary device. So that device will provide the current measured. So the advantage is it has got a wide range of measurement compared to a conventional CT, a current transformer. The conventional current transformer will have an issue called saturation. Okay, most of you may be aware, if the current goes beyond certain value, the core of the current transformers will get saturated and the output ceases to zero partially over a half a cycle waveform, which is a major issue for any protection engineer like me, who are working day in day out with these electromagnetic CTs. So the COSI sensors has an advantage that it provides the output with good accuracy, and it can even provide up to 250 kiloamperes if it is designed with that particular parameters. So one is the accuracy is better, and the range of measurement is wide, uncomparable, and the deviation with respect to temperature is also not that high, and it will give an output on 650-9-2, which is a standardized um, protocol. That protocol is fully interoperable with any other similar device. Okay. So having said that, The output can be used in the Ethernet layer for multiple instances at multiple locations. Of course, it is sustainable and it is less in weight as well. And once we have COSI, we can use this particular output for multiple functions. For example, if you want to measure the harmonics, you can measure the harmonics. And there are different classes. If you want to have high accurate, low range data, you can have it. Or if you want to have higher data, or you can say a broader range, but which you want to have a better range for the protection functions, that is also possible. So where you can have a full settable options across the sensors. Okay. And it is accuracy wise, it is 0.1%. So mainly the moment I say accuracy, accuracy corresponds to the revenue when it
भैया
comes
ये
to
ग्लास इधर
generating
रखा
station.
कंप्यूटर टेबल के पीछे साइड को.
Can you please, I think the coordinator can have some settings to have muted all so that it will not disturb everyone, right? Okay. So we will have a wide range of measurement, and you can see the measurement starts even from 10 milliamps. So this is used for certain applications where you need to really monitor a very low measurement for open pole detectors, and it can go up to 500 kiloamperes, which are used for specific applications. Okay, and it is fully immune to any induced EMF from the neighboring phases, or it can be a geomagnetic flux induced measurements. So it is fully immune to that. So in that way, it is much accurate, and you can say it's environment friendly for the applications. So this shows how it works compared to a conventional CT. So the one in blue is a non-conventional instrument transformers. You can see the accuracy starting from the range from 1% to 100%. Accuracy is far better than the conventional one. So even if you have 0.3 class, 0.2 class, 0.515 class, it's all far different. But the accuracy, what you can see for the non-conventional instrument sensors are definitely good. So let's go to the application. This is an actual switch gear which has got the COSI sensor as a part of the switch gear itself. So this is a switch gear compartment, and this has got the COSI CT which is mounted in the same pole. So whereby you have a full advantage of having the space advantage, and also you have, of course, the advantage in terms of the pricing, because you don't require a separate space for this particular CT, which usually conventionally you will have a separate pole for CT. So here you can see this is a breaker. The same breaker has got the same CT in it. Instead of having a separate space, and this will save more space for us as well. Okay, so it has multiple advantage in terms of space, in terms of weight, and in terms of accuracy. These sensors has got a lot of advantages. So now we will see how it is applied for a air insulated substation. The typical look and feel will be like this. So the sensors are inside. So you have the CTs, then you have a combined design. So combined measurement optical unit, that's called the CMO. It will have combined voltage transformers and the current transformers. Both are in the specific single pole combined for the measurements. So how that works? So you will have a capacitive divider. Okay, so the capacitive divider is essentially in this particular insulator. What you can see here, the insulators. You will have capacitors inside, and you will have Pockle sensors. Okay, these Pockle cells act as a sensor, and this CT is a typical Faraday sensor which we have seen. And Pockle cell sensors are part of this particular
पानी बोला.
capacitive divider.
दे.
Capacitive divider. Okay, so this capacitive divider, we will have the drop of voltage, and the Pockle cells will measure the voltage, and it will provide output. So the output from the Pockle cells will be a fiber, and this particular XMU device will be a numerical merging unit, and these merging units will convert the information to the highly accurate voltage measurement. So this will have voltage measurement and the current measurement available in the same device. Okay. So this is how a glass ring Pocal cell looks. So this sensor works on a simple principle of Pocal's effect, where you will have, okay, I will show in the next screen where you will have, what is this? Okay, so this is how a Pocal's voltage sensor works. So what will be applied to the voltage as a voltage to the Pocal cells is here. Suppose after the CVT here, after the CVT, let's assume you have 1% of the total voltage. So if this is 110 kV and 1% should be ideally 1.1 kV. Why I'm hearing noise? Can you mute him? Hey, can you mute? Actually, I'm continuously hearing some knocking noise. Can you hear me, Ayapa? Someone can mute him. Maybe he's kept his mic on. Okay. So once we have this capacitor divider, then we have this particular output all the way coming up to the Pocal cell. So the Pocal cell will have this specific voltage applied to the cell. So in this scenario, if we apply a polarized light, so this particular light will have a phase angle difference based on the voltage what we applied across this. So indirectly, this particular Pocal cell will give an output based on the voltage applied here. Suppose if you're applying 1 kV, it will be different voltage. If you're applying 5 kV, it will be different voltage. And based on the voltage, you will have output which can be directly calibrated and which can be taken as a measurement all the way in your system. Okay. Epa, can you ask, I think, can you force them to mute? Can you hear me?
Yes.
Can you ask him to mute it, or can you do something?
Okay. And your
Or in the event
participants
set,
kindly mute your mic. Rajesh Anand, kindly unmute and speak, please. Kindly
okay,
unmute.
fine.
Okay.
Okay, fine.
Thank you. Thank you.
Yeah, now it's clear. Okay, so this is for the AIS, and when it comes to GIS, it's a gas insulated substation. So this is a look and feel of the gas insulated substation, where you have all the chambers of gas insulated bus bars, and then you have the CTVT in it. So what we will be doing is a typical bay for a GIS. Then we have the sensors in the GIS. The one which we have seen in the previous slides are AIS, air insulated substations. Okay. So in the air insulated substations, we will have all the sensors like what you have seen as a CMO, or it will be in the open air and the open environment. But however, in the GIS, it's all encapsulated, enclosed switchgear, gas insulated switchgear. So then we have to mount all these sensors well inside the switchgear compartment. So we have options to have the devices sensors mounted inside. So we can have voltage sensors, we can have current sensors mounted inside. So this is a full mechanism of the gas insulated switchgear. Yeah, let's further break down how the sensor works inside the chamber of GIS. So we'll have the Rogowski's current sensor inside this, and then we will have voltage sensors this inside the compartment as shown below. So this one will be very compact in terms of size. It will reduce drastically, and you do not really require a separate chamber for a current transformer and a voltage transformers. It will be very compact, and the weight wise also it will reduce by 10 to 15%. Okay, so how a Rogowski sensor works? So we will have a Rogowski coil outside the primary conductor, and the formula of voltage is proportional to current. Okay, so the cross sectional area, so the rate of change of current with the given cross sectional area, there will be an output, and that output will be given and to the device where it will be calibrated to measure the actual current in the conductor. So this is how we measure the actual magnitude of the current indirectly using the Rogowski sensor. So we will have the voltage and it will be very much accurate, and we do have our own Rogowski sensors to measure the current using this particular principle. So how it is mounted inside, this is how it is mounted. You can see here that is a Rogowski coil inside the equipment. It will be encompassing your primary equipment. So this is a R phase, Y phase, B phase. In the three-phase system, this is actually encompassing here and this is encompassing here, and it will provide the full measurement of the current. Similarly, for the voltage, there will be a CVT, so capacitive effect voltage transformers. So where the air will act as a C1 or CHV, okay, it's a dielectric. Then you have another capacitor which you will have here, and the output will be coming all the way to the sensor device here. So the primary voltage and secondary voltage, there will be a fixed relation, and the measurement will be given directly to the sensor device here, and then further the output will be given in the Ethernet TCP/IP 650 format. Okay. So we have seen both the current-based sensors and voltage-based sensors, and in both um, air insulator substations, and also we have seen in gas insulator substation as well. So now you can think, after doing this, what my substation network, how it will be looking like. Instead of having hundreds of wires, you will be having only a couple of fibers to the device. Okay, so a couple of fibers coming to the device. You can see, you can imagine this particular white one, like a SCU, or there is a protection device which is in the middle. Okay, which has got two fiber optic links, one from the bottom and one from the top. One from the bottom is a process bus. Process bus is the sampled values which comes from the non-conventional instrument transformers and the sensors. Okay, so from these sensors, this is all called the process bus. Usually, it comes in 90 samples per cycle. So these sensors are further calibrated, and the further output is made in such a way that the output will be in the Ethernet layer with 90 samples, sorry, 80 samples per cycle. Or if you require the data at a higher frequency sampling rate, then you can also have a 256 samples per cycle. The one on the bottom is a station bus. So the station bus is for the controls where you can exchange the measurements, parameters, controlling, opening, closing of the breakers. So this will come from the station bus. Then you have got two bus called the process bus from here, which is all the essential current and voltage parameters from the sensors, and the one on the top, which is the station bus for the controlling. So it will have a full Ethernet based substation where you have all the highly accurate digitized substation. So that's why we call this as a digital substation. So I hope you've got an idea how a sensor like a Rogowski sensor or a quasi-optical sensors or a CVT sensors are used in digital substations, and how it is implemented in a real world in a station where you have protection and control devices. So this is for the digital substation when it comes to the sensors for the current and the voltage. And in the next half, we will be discussing about the sensors used for monitoring and diagnosing the station equipments. Okay, so here we will be talking about more about transformers. In transformers, what are all the several sensors which are used to improve the reliability and reduce the downtime, and to have a full maintenance based observation based or data based maintenance rather than having a periodic maintenance. Okay, so condition based monitoring and condition based maintenance is essential for efficient operation, rather than going for every 2 months, 3 months, 1 year, and doing the oil change, doing the maintenance is not required. So based on the usage, based on the real issue, it is better to go for the maintenance. So how we'll collect the data using advanced sensors in the transformers, and whereby the data will be used to take a decision, and your controllability of the machines will also be better. This particular slide shows the typical cause for the failures in the transformers. The transformers are essential part in the substation environment, and in case of a failures of transformers, we will lose a big network. And transformers failures are hazardous in nature. Usually, it causes fire, which we have seen quite often. Transformer fires are difficult to quench because of the nature of the oil inside the transformers, and oil coming out of the transformer will feed the fire further, and it can cause a major disastrous effect. Okay. So it is important for us to identify using our advanced sensors. So this shows a bathtub curve, how a life of transformer is with and without monitoring. So if you are not at all monitoring, it fails well before its lifetime, and we do regressive maintenance, but at one fine day it will fail even without our control. But with monitoring, you do not really do much of the maintenance, but you will have a clear understanding what's going to fail, and you can attend it well before it fails. And you can always save the transformers and improve the life of the transformers. That's a whole idea about having this application. Why a transformer would fail? Because of the insulation failure, breakdown of the oil, and various other factors. So first is we'll be analyzing the gas in the oil. Okay, so dissolved gas analysis is an essential part to understand what could have gone wrong inside a transformer and where we are. Are we closer to a failure? Okay, so we have got several gases like hydrogen, methane, ethane, ethylene, acetylene, carbon monoxide, carbon dioxide, oxygen. By having a clear understanding about the specific gas composition in the oil, we can easily predict what type of fault it is happening inside. For example, if you are having more arcing inside a transformer, so in that case, you will have more acetylene. Okay, so acetylene is a direct indication of that. When you have a CO2 to CO ratio in a unusual range, possibly there is a failure of the papers. So there is a ratio called CO2 to CO. And conventionally, how we do it, we used to go to the station, we used to tap the oil, used to bring to the lab, then we used to see, check it. So there are a lot of disadvantage. Someone has to go, and there are many unmanned stations where it operates without any human interference for months together. And there we need to have a sensor which will periodically measure and provide us an information. And moreover, bringing it to another location, different containers, it will contaminate. You have to bring it to the open atmosphere. Then the moisture of the open atmosphere affects the quality of the oil sampling and the test results, obviously. Okay. So critical gas, we have got acetylene and ethylene, which is mainly for hot temperatures and arcing inside. And of course, hydrogen is also important, where you have got a partial discharge inside the transformers. So we need to really monitor hydrogen, methane, ethane, carbon monoxide, plus acetylene and ethylene are very important. Plus carbon dioxide, oxygen, and nitrogen. If it is a very big transformer, like for you have a big generators of 500 MVA transformer, then it is very common to have that advanced gases as well for monitoring. So the reason behind these particular failures could be of aging. Okay, it's a age transformers. It could be because of the oxidation of the materials, what it is happening inside. And partial discharge is something which happen inside the live conductors. Okay, so when you have a partial discharge in the oil, our hydrogen content in the oil will go up. Okay, so it is also important to see if there is a hydrogen content. What is hydrogen content? Hotspot is, suppose if there is a small damage of the core inside the transformer, the core damage will eventually lead to some kind of a eddy current, localized eddy current, causing to have a red hot locations or very high temperature location inside the transformers. At a short run, maybe it may not have an issue, but whenever during the evening time, if the load is more, this fringed flux in the causing the eddy currents in the damaged core can aggravate it and cause a bigger failure in the core, leading to a short circuit and a fire. So when we are able to detect that when it is at a lower value, it is easy to identify and attend to that and resolve the problem. And for the transformers, important sensors what we need is in the OLTC, so on-load tap changers. are coming with the sensors, particularly for dissolved gas analyzers, PD sensors. We have online sensors to monitor that. So this shows the full fleet of the sensors what we have. For example, if you look at, we can have only hydrogen sensors, and you can have multiple gas sensor, 3 gas, 5 gas. Okay, so these are all the product names. You need not really um, look at it, because you can always search in the internet. You will find a lot of documents and from our website. But this gives an idea based on the size of the transformers, what type of analysis is required. So I need not really go for a 9 gas analysis for a smaller transformer. But at the same time, if it's a very big transformers, very important 1000 MVA transformer in a super thermal power plant, you may require a 9 gas analysis with a lot of thermal cameras to have it monitored, and it will safeguard, and we will save millions out of it. Because one failure of one big generator transformer can lead to 6 months or downtime or 1 year downtime easily, losing the full generation. Okay, so it's worth to have these sensors rightly placed and rightly commissioned. How it looks. So this is a simple device called a hydrant. So this device is mounted at the right corner. You can see a small valve which is used to sample the oil. Okay, automatically it takes oil inside and it checks for the hydrogen. So in what principle it works, that I will show. So here you will have this mounted, automatically it takes and measures and provides the reading over the TCP layer or any other protocol which you would like to have. These are all actually mounted on the open transformer wall. So nowadays the transformers are coming with these provisions for these sensors, either at the source of the transformer manufacturing itself, or there will be a wall given for the user to mount this separately once it is commissioned in the station. So we have option to do either in the manufacturing stage, or you can also do it at this time of commissioning later in the station. It will give output contacts. It will have communication. So it's all very intelligent. It is fully IP rated for all extreme environment, high temperature, and the sensors are very, very accurate. It can have gas sensor, moisture sensor. So you will see what all the type of sensors we have. And these devices will give precise information, and we can plot as a trend. And you can also separate, have a HMI screen to monitor hundreds of transformers from a control center. So these sensors provide very vital data, providing the information about the healthiness of your substation and your fleet of primary equipments. So this look and feel of a bigger DJ 900, which has got photoacoustic gas analyzer. So how it works, how this sensor works. Okay, so these sensors will have inlet oil, and it will also have an outlet oil. You can see the picture. So the oil will enter and the oil will come out. So it is not, you are not going to discard, or you will not really throw the oil away. So the oil can just come in periodically, maybe once in a day or once in 12 hours you can do it. So the PGA, that is photoacoustic gas analyzer, will take the oil, and this is how it works. So it takes the infrared source, okay, and it will send the infrared source at a specific wavelength, and it will give a pulse. It will be pulsed. You can say it's a pulsed IR light, okay, and it will be sent across the oil to see what gas is contained in the part of the particular oil sample what we have taken. So based on the type of oil, we will have different type of output, or you can say it will be converted to a acoustic signal, by which will be monitored to see what type of gas is dissolved. Based on the type of device which we are using, you can have a multi-gas analysis, and it will give a full trend of the gas dissolved in the particular oil. So you can mount this at different locations, but particularly when it comes to a transformer, we need to protect the transformer against several faults, considering these key 6 segments. Okay, so one is the DGA, what we are discussing now. Thermal model, what is the actual temperature with the current, with the load temperature. Partial discharge. Then we monitor the bushing. So there are called bushing sensors. So those sensors monitor the healthiness of the, you can say, tan delta or the capacitance of the bushing. Then of course, on-load tap changer is a very, very critical place where you will have multiple failures or observed in all node temperature. At least you can say almost 1/3 of the transformer failures, big transformer failures, happens in the OLTC chamber. And of course, we need to really closely monitor the cooling efficiency of the systems as well. Okay. So first we have discussed about photoacoustic gas analyzer sensors. Now it is a bushing analysis. Okay. So in bushing analysis, there will be bushing probe points where we can check the bushing strength. Okay. So we can always check the bushing capacitance value, and we can also check the tan delta value, power factor of the devices. We can always monitor the capacitance of the particular bushing. And in case if you have moisture, then we have a separate moisture sensor, which will work in parallel to the bushing monitor. And in the bushing monitor, we will completely check what is the capacitance value. And there are several methods, like you have a UHF based method. And there is one more method of the real-time measurement of capacitance using the voltage itself. Okay. So in any specific bushing, if you see, there will be a data mentioned like this. So how much picofarad it is and how much voltage is this. So it shows it is a typical 176 kV. I think it was used for 132 kV application, and it shows the capacitance value of C1, C2, and CX. So the device can be calibrated to monitor if there is any change in the capacitance. The sensor can be programmed to give an output, and it can also have a trend. Okay, so this is how it will be. So you have the sensor probe, and from the sensor probe for R phase, Y phase, B phase. So normally conventionally in India we call RYB. Sometimes it is called as UVW. So we call RYB. And then we can have bushing monitoring devices where you can monitor the current which is flowing through the specific leakage current flowing through the capacitance, which is nothing but your bushing. Bushing is actually a dielectric capacitance. Okay. And then we can monitor the change in capacitance over a period of time, how it is getting degraded. And this will be plotted, this can be plotted in a graph. And this can also be given for any kind of maintenance alarms or to take any precautionary measures as and when required. So having said that, we can also have a look at the tan delta. So tan delta usually we mention in terms of percentage instead of the decimal value. So the tan delta value can also be monitored continuously, and we can give an alarm using the same technology. So that's a highlight of these sensors, that it's all real time. So it will provide real time information, and it will also monitor. The moment we have single phase measurement, then you can also monitor the interface measurement as well. So interface measurement means you can check the tan delta between two phases. So, and you can also plot. You can plot ROIB plotting, and you can see where your tan delta angle is. So that can always be monitored. Okay. So this shows if there is any change, it will give an alarm, and you can always see how the interface is, face to ground how it is, face to face how it is. So the sensor will always provide the detailed information in a live format, like how it is shown here. Okay, so it will give a full information about the percentage of the tan delta over a period of time. So this shows how the relative power factor percentage, or you can say the tan delta power factor, del power factor has changed. Um, if there is any relative common change happening, it will give an alarm, and it will also give the healthiness of the system over a period of time, or maybe because of the load if it happening. So you will have a clear picture since the data are all cold and it is in the trend in your system. It is always available for your diagnostics. Then it comes the partial discharge as well. So if there is a partial discharge deterioration, these particular sensors can count the number of partial discharge happening. Okay, so whenever there is a partial discharge happening due to high voltage, you can always have an count of it. Okay, and we can also try to predict where it comes from. So we need all the probe points to see where we can really measure those kind of PD discharges, and it will give a full information about the PD data, how much time it was there, and we can also lead it to some failures, and we can always diagnose that and provide a recommendation from the system itself. So we'll also discuss about system, how that works. The system will contain the full picture of your substation. So we will also see a big eagle's eye view on your complete network, and you will also see trend. And you can also compare between two transformers. In a size station, you will easily find 5 to 6 transformers of the same size, or maybe in your fleet in a utility, they will have almost the same size of transformers, 10, 15 transformers in their network of the same size. If you have the data of 10, 15 transformers, one is if it's odd one out, then you can easily compare, okay, why other transformers of the same rating, same make, almost commissioned at the same time, it was not having this particular parameter in this fashion. So you can always try to understand. You can also have some kind of AI based APM. So we call it as a asset performance monitoring, which includes AI in it, which can compare from one to another as well, to provide a meaningful data for you if there is any degrade of the transformer. Okay, using these sensors. This how a bushing probe will be. Just would like to share the picture of it. So this is a probe available here, and you can always access to it, and from there you will get the data for your diagnosis. So moving forward, then we have further other sensors which monitors the ambient. So why ambient is required? For example, if the temperature is around 5 degrees, 10 degrees, my cooling fans need not run, or maybe only few cooling fans shall run. So we need to monitor the temperature, ambient temperature, oil temperature, winding temperature. So you have multiple other sensors which can also be provided uh, which can also be provided. So you have top, bottom sensors, you have load sensors, you can also see how much current is flowing. You can keep a thermal model. So that's why we call it a thermal pack. Thermal model means you can have a thermal imaging using the current. So current causes the temperature. So we can, in turn, we can calibrate the temperature of the transformer itself using the current. So if you have the full heating time constant, so it's not a homogeneous material, we can try to arrive using the IEEE standard for the winding and the oil. So there is a heating time constant for oil, there is a cooling time constant for oil. So you can do it. But if you have the live temperature, it's much more accurate, and you can have all the temperature probes and the sensors which will all the way come to this particular device. Normally we provide sensors for load, temperatures, top oil temperature, bottom oil temperature, then we have winding temperature as well. Cooling current sensors, even if the oil temperature can be directly measured, you can even monitor the cooling fans. You can even switch from one fan to another fan. You can switch in groups. So there are a lot of AI based cooling methods you can have it. And we can also see the cooling efficiency, how much is the inlet and how much fans are running, why the output oil is having that much current. So you can always monitor that as well from time to time, how our cooling efficiency is. Even we can monitor the cooling fans, cooling bank. So you can switch from one bank to another bank. You can do a lot of AI based methodology for this. And then we have the OLTC based. So OLTC, as you know, we monitor and change the taps based on the loads. Okay, so based on the voltage, we change the taps, which is usually in the high voltage side. So based on the voltage, based on the loads, the voltage changes, and of course you can change the tap, and it is prone for failure as I was mentioning earlier. So we can always have a sensor to see the tap position and compare with the parallel transformers. And if there is any arcing, you will always have the DGA. So that will be a dedicated DGA called, we call it a tap trans. So that will be mounted in the OLTC chamber. I will show the OLTC picture, that then you will have an idea. Okay. So this is a OLTC without an oil. Okay. This will be fully been immersed in a tank. So this is a transformer inside. This is the picture. And you have the tap from the high voltage where the OLTC will move. It's on-load tap changes. So since it moves during the normal operation with the heavy load, the arcing will come. So you need a DGA, particularly like ethylene, acetylene, hydrogen, to monitor that. So these sensors will see, it can count the number of OLTC operations, it can count the gas in that, it can even see the torque of the motor. So it can, there are sensor to see the torque of the motor, how many times the tap has changed, because it has a maintenance duty cycle based on the number of operations. In some locations, the OLTC operates quite often. And then in that case, we need to go for maintenance after a certain number of operations. So there are sensors in the OLTCs which will monitor the gas, the number of operation, arcing. Of course, we can also have a PD in it. Then we have the thermal sensors. Now the current advanced technology is the current sensors, thermal sensors. So after having all the gas sensors, if you can recollect what we have discussed, we have got a gas sensors, we have got a moisture sensors. Okay, so that will be based on the capacitance. We have moisture sensors. Then we have the OLTC sensor, bushing sensors, temperature sensors. Now we have thermal camera based sensors. Okay, this is advanced technology what we are deploying. So it will give a full picture of a transformer in a thermal model, and it can correlate with the load. With the load, if maybe some temperature is acceptable, but if my load is only 10%, if some areas is showing abnormal, so it can have some kind of analytics based on the load and where the thermal content is more. So based on the infrared cameras, it will detect which portion is having. If you see here, the one on the left bottom, the middle phase has got a different temperature than the other two phases for the same load. Of course, loads are normally balanced. So it is having a different temperature here. Okay, so these sensors will help us to really identify and act immediately, because this transformer would have been even gone for a maintenance a week back. But what we would see, because of some small loose connections, like in our house, if you have a loose connection in your switch, of course the switch will run out and it will have an arcing and it will fail, maybe a new switch. Okay, so it can happen for anywhere. So it's not necessary to be a new or old. That's why the condition based maintenance and alarm will help us. Even a premature infant stage failure can be avoided here. So these are a typical example with 3 thermal cameras which will be wired here. Then we will have the full picture and the topology and the understanding of the transformers layout. Then you will have a graph like this. So what is the temperature on the lower part? What is the temperature at this point? So you can calibrate it. So if based on your interest, you can see where which point is of your interest. You can plot it. Then this sensor data will be processed and it will provide an alarm based on the observations. Okay, so it will give alarm. Okay, this specific area of this is having an alarm, and you can also see over a period of time. In summer with the same load, last year this camera, with the camera we can identify the temperature was X and today it is Y. So you can also see a variation from year on year, not necessarily from yesterday to today, but year on year for the same load. We can always correlate and we can generate a report. So it will give a full fleet of information for the transformers. Okay, and this is a look and feel where it is mounted. You can see here this encircled area has got 3 cameras and which is wired all the way here. Okay, so these cameras will be 24 hours monitoring the temperature across the full transformer, and it will give a valid vital information for us to go for maintenance. Okay, so that's all for the sensors in the digital substation, what we have in the real network. Just to summarize before we close, so we started the session with the digital substation. Then we were discussing about the digital substation sensors. Okay, just a second, I will switch to the first slide. Okay. So we were discussing about digital substation, and we were discussing about current sensors, voltage sensors, um, Cauchy sensors based on Faraday's effect, Pockels effect. Then we were discussing about the digital substation advantages in terms of accuracy, in terms of weight, in terms of safety, sustainability. Then we move to digital substation advantages and how the digitized quantities is helpful for very accurate measurements, monitoring, PMU, phasor measurement unit at a control center level. Then we switch to the monitoring and diagnostics in advanced digital substation using several sensors, sensors like temperature sensors, moisture sensors, dissolved gas analyzers, various gas which are cause damage to the transformers. And we discuss about the OLTC, and we discuss about thermal graphs, thermal cameras as well. Hope you find it helpful and interesting. Let me know if you have any questions or we can discuss.
Participants, if you have any queries, you can now ask.
Hello.
Hi.
May I ask the
Yeah, yes,
question?
please.
Yeah. Okay. Thank you for your nice talk. I would like to ask about the thermal
Yeah.
camera. Actually, your camera is in open space, and what I know is like if you have a reflection, and you need to insert the emissivity also to get an accurate temperature. So, how you ensure that your temperature which you are getting from thermal camera is correct?
Okay. Yeah, of course,
Because
that
you are not avoiding
calibration
the.
will be, yeah, yeah. See, that is
Uh,
the reason in the daytime where we have higher emissivity or reflection, sometimes it may not be accurate. So, so we always calibrate, or we used to compare with the results in the night times. Okay. And of course, in the daytime, we have higher reflectivity or some influence of the external factors. It will be calibrated and it has to be addressed. So that's a challenge which we normally face, and it will be handled with the proper calibration, and some kind of filters are also used. And that's one of the main reason these cameras will have a specific location. Sometimes certain locations will not give a correct reading. So based on several other factors, we used to do it, and we rely on several other factors to make sure that the data what we are getting is not influenced by various other environmental factors like what you said.
okay. And how much error you are expecting? Like, is it okay for you?
Thermal cameras is more of errors. Normally, what we are seeing is not more than 5 to 10
Okay,
percentage. So, but with the required filters and the proper commissioning, this should not have an issue.
okay, sir. Thank you. Thank you very much.
Yeah, you're welcome.
Participants, any other queries? Kindly you can ask. Is there any other queries? Participants, you can kindly type in the chat box about feedback about the session. You can type feedback. Thank you, sir. You can type your feedback in the chat box too.
No queries, sir. Very neat presentation.
Okay,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.
Thank you, everyone.
Thank you. Wait a minute. Wait a minute.
If I can close.
So Rajesh Anand, thank you so much for the presentation was very good, nice, and was so much informative. So thank you so much, sir. Thank you.
Thank you. Thank you.
Thank you.
Bye.
Thank you so much.
Bye, everyone. Thank you, everyone.
Talk to you later.
Yeah.
Participants, kindly fill the feedback for the both sessions that we have posted. It has been posted in the chat box. Kindly fill your feedback, please.
Thank you, everyone. See you.
So, okay, thank you so much.
Bye.
Bye.
Sarah.
Wait a minute, wait a
Kuprama.
minute. I
Bye.
will turn on my camera. So,
Bye.
thank
Bye.
you so much, da. Thank you. Bye.
Bye. Bye.
Thank you. Participants, the feedback link has been put in the chat box. It will be open till 10 p.m. and we will be closing the meeting link by 8:35 p.m. So kindly fill in the feedback within that time. Thank you.
Dear coordinators,
Yes, sir.
kindly send the sir. Kindly yesterday session was very nice, sir, and kindly send the PPT, sir, and also
Okay,
today's
sir.
session.
Okay. Okay. PPT.
Thank you, sir.
Thank you, sir. Thank you.
Sure, sir. The PPT will be shared in the WhatsApp group. Thank you, sir.
Participants, again, kind reminder to all of you, tomorrow's session will start at 2 p.m. So kindly make a note of that. We have also put the same in the WhatsApp group about this. Kindly make a note of that. Test timing is 6:30 p.m. to 7:30 p.m. Thank you.